Right now, somewhere in the universe, two neutron stars are about to collide. Each one weighs more than our sun, but measures only 12 miles across. When they crash, they will release more energy in 1 second than our galaxy produces in an entire year. But this kilonova explosion is just the beginning. We are about to witness stellar corpses that fire gamma-ray beams across billions of light years, black holes that devour entire solar systems, and cosmic events so violent they could reshape reality itself. If you want to see how powerful the universe really gets, hit that like button and subscribe. Prepare yourselves. We begin. A bolt of lightning tears through the sky above your head, carrying 5 billion volts of electricity. This single flash heats the air to 50,000 degrees F. That is 5 times hotter than the surface of the sun. The thunder you hear afterward is actually a sonic boom created when superheated air expands faster than sound itself. In less than 1,000th of a second, this electrical discharge has unleashed enough energy to power a typical American home for an entire month. But how does nature create such incredible power? Picture the atmosphere as a massive battery that is constantly charging itself. Storm clouds act like towering electrical generators with ice particles and water droplets colliding billions of times. Each collision strips away tiny electrical charges, separating positive and negative particles like a cosmic game of static electricity. The top of the cloud becomes positively charged, while the bottom turns negative. Meanwhile, the ground below develops a positive charge that grows stronger as the storm builds overhead. The electrical difference between cloud and ground creates an invisible pathway through the air. Think of it like stretching a rubber band tighter and tighter until it finally snaps. When the electrical tension becomes too great, nature finds the path of least resistance. The lightning bolt we see is actually electricity racing both ways at once. A nearly invisible leader stroke creeps down from the cloud, testing different paths through the air. When it gets close enough to the ground, a return stroke rockets upward at 1/3 the speed of light. This return stroke is what creates the brilliant flash we see and carries most of the electrical current. Some lightning bolts stretch over 100 meters long. Others strike the same spot multiple times in rapid succession, creating the flickering effect we sometimes observe. The most powerful lightning ever recorded carried over 300,000 amp of current. To put that in perspective, a typical household electrical outlet delivers just 15 amperes. Lightning kills about 25 people in America every year and starts thousands of wildfires. But it also serves a crucial purpose for life on Earth. Every lightning bolt creates nitrogen compounds that fertilize soil when carried down by rain. Without lightning, many plants would lack the nutrients they need to survive. In some parts of the world, lightning strikes the ground over 200 times per minute during peak storm season. Lake Maracaibo in Venezuela experiences lightning almost 300 nights per year, making it the most electrically active place on our planet. Yet, for all its devastating power, lightning represents just the beginning of nature's electrical fury. The energy in one lightning bolt seems enormous until you consider what happens when our sun decides to unleash its own version of electrical violence. But those solar storms operate on a scale that makes earthly lightning look like a tiny spark. The most powerful weapon humanity ever created turns sand into glass across an area larger than Manhattan. When the Tsar Bomba detonated over the Soviet Arctic in 1961, it released the energy equivalent of 50 million tons of dynamite. The fireball alone measured over 2 meters across and could be seen from 600 meters away. The mushroom cloud rose 39 meters into the atmosphere, 7 times higher than Mount Everest. Windows shattered in buildings over 500 meters from ground zero. But what makes nuclear weapons so catastrophically powerful compared to conventional explosives? The answer lies in the very heart of matter itself. Traditional explosives work by breaking chemical bonds between atoms, like snapping the connections in a complex house of cards. Nuclear weapons do something far more fundamental. They actually split atoms apart or fuse them together, releasing the enormous energy that holds the nucleus together. Think of an atom like a tightly wound spring that has been compressed for billions of years. When you split certain heavy atoms like uranium or plutonium, that spring suddenly uncoils with incredible force. In nuclear fission, one atom splits into two smaller pieces, releasing neutrons that crash into nearby atoms and split them as well. This creates a chain reaction that spreads through the nuclear material and microscopes Einstein's famous equation that energy equals mass times the speed of light. Since the speed of light is enormous, even tiny amounts of matter convert into staggering quantities of energy. A single pound of uranium contains as much energy as 1,400 tons of coal. During the first nuclear test in New Mexico, scientists were not completely certain the chain reaction would stop. Some worried it might ignite the entire atmosphere and destroy all life on Earth. Fortunately, their calculations proved correct, but the explosive yield still exceeded their predictions by 30%. The heat at the center of a nuclear explosion reaches 100 million degF. That is 6 times hotter than the core of the Sun. The initial gamma radiation moves outward at the speed of light, followed by an intense thermal pulse that can cause third-degree burns 15 meters away. Then comes the blast wave, a wall of compressed air traveling faster than the speed of sound. Modern nuclear weapons use a two-stage design where a small fission bomb triggers an even more powerful fusion reaction. These hydrogen bombs forced light atoms like deuterium and tritium to combine into heavier elements, releasing even more energy than fission alone. The largest weapon ever designed by the United States had a planned yield of 25 megatons, but was never tested at full power. However, nuclear weapons pale in comparison to the explosions happening naturally throughout our solar system every single day. Our Sun converts 4 million tons of matter into pure energy every second through nuclear fusion. But even our star's constant nuclear fire seems gentle when you witness what happens when solar plasma decides to break free and hurtle toward Earth at millions of miles an hour. Beneath Yellowstone National Park, a chamber of molten rock the size of Los Angeles sits just 5 miles below your feet. This supervolcano has erupted 3 times in the past 2 million years, and each explosion was thousands of times more powerful than any nuclear weapon. The last eruption, 640,000 years ago, ejected enough ash and debris to bury the entire state of Texas under 3 feet of volcanic material. The ash clouds circled the globe and blocked sunlight for years, triggering a volcanic winter that changed Earth's climate. Volcanic eruptions happen when the incredible pressure of molten rock called magma finally overcomes the solid crust above it. Picture the Earth like a pressure cooker filled with liquid rock heated to over 2,000 degrees F. Just as steam builds pressure in a pot until the lid blows off, magma finds weak points in the rocky shells surrounding our planet and explodes toward the surface. The most explosive eruptions occur when gas-filled magma encounters water or when the magma itself contains high levels of dissolved gases. As the molten rock rises toward the surface, decreasing pressure causes these gases to expand rapidly, like opening a shaken bottle of soda. The result is a violent explosion that can launch rocks the size of cars over 20 meters into the air. Mount Vesuvius famously buried the Roman cities of Pompeii and Herculaneum in 79 AD, preserving them under layers of ash and pumice. But that eruption was relatively small compared to what volcanoes can really do. The 1815 eruption of Mount Tambora in Indonesia killed over 70,000 people and caused global climate chaos. Crops failed worldwide, leading to famine, disease, and social unrest across Europe and North America. The most powerful volcanic eruption in recorded history happened in 1883 when Krakatoa exploded with the force of 200 megatons of TNT. The sound of the explosion was heard 3,000 miles away, and the pressure waves circled the Earth 7 times. Tsunamis generated by the blast reached 130 feet high and killed over 36,000 people across Indonesia. But terrestrial volcanoes seem almost gentle compared to the volcanic activity we observe on other worlds. Io, one of Jupiter's moons, experiences volcanic eruptions that shoot lava fountains over 250 meters high. That is 50 times higher than any eruption ever recorded on Earth. The low gravity and thin atmosphere allow volcanic plumes to reach incredible heights that would be impossible on our planet. Some volcanic eruptions on Io release sulfur dioxide at temperatures exceeding 3,000 degrees F. These alien volcanoes are powered not by internal heat like Earth's volcanoes, but by the constant gravitational squeezing from Jupiter and its other large moons. This tidal heating keeps Io's interior molten and drives continuous volcanic activity across its entire surface. Yet, even the most violent volcanic eruptions we have observed still cannot match the raw power that our sun releases when it experiences a really bad day and decides to hurl billion-ton clouds of plasma directly at our planet. A twisted loop of magnetic field on the sun's surface suddenly snaps like a rubber band and releases the energy of 1 billion hydrogen bombs. This solar flare erupts from a region called a sunspot, where magnetic field lines become tangled and stretched until they can no longer hold their shape. When these magnetic structures finally break and reconnect, they launch high-energy particles and radiation across the solar system at speeds approaching the velocity of light itself. The largest solar flares ever recorded belong to a category scientists call X-class events. Think of the sun's magnetic field like invisible rubber bands stretched across its surface. During periods of high solar activity, these magnetic field lines twist and tangle as the sun rotates. Different parts of our star spin at different speeds, with the equator completing one rotation every 25 days, while the poles take 35 days. This uneven rotation winds up the magnetic field like a spring until something has to give. When magnetic field lines with opposite polarities get close enough, they suddenly snap together in a process called magnetic reconnection. The energy stored in these magnetic fields converts instantly into kinetic energy, heating plasma to temperatures exceeding 20 million F. Solar flares accelerate particles to nearly the speed of light and send them racing across 93 million miles of space toward Earth. The most powerful flare ever directly observed occurred in 2003 and was later classified as an X-28 event. This monster flare saturated the sensors designed to measure it, meaning its true intensity was probably much higher than we could accurately record. When solar flare particles reach Earth, they interact with our planet's magnetic field and atmosphere in spectacular ways. The charged particles follow magnetic field lines toward the poles, where they collide with oxygen and nitrogen molecules in the upper atmosphere. These collisions create the beautiful auroras we see dancing across the sky in green, red, and purple curtains of light. But solar flares can also cause serious problems for our technology-dependent civilization. The high-energy particles disrupt radio communications, damage satellites, and can even affect power grids on Earth's surface. In 1859, a massive solar storm called the Carrington event caused telegraph systems worldwide to fail. Some telegraph operators received electric shocks and telegraph paper caught fire in multiple locations. If a Carrington-level event happened today, it could cause trillions of dollars in damage to our electronic infrastructure. GPS systems would fail. Internet communications would be disrupted and power grids could collapse across entire continents. Airlines would have to ground flights to protect passengers from radiation exposure, and astronauts on the International Space Station would need to take shelter in specially shielded compartments. Solar flares typically last only minutes or hours, but their effects can persist for days as charged particles continue streaming through the solar system. However, these individual flares are nothing compared to what happens when our sun decides to launch an entire chunk of its outer atmosphere directly toward Earth at speeds exceeding 1 million of. 1 billion tons of superheated plasma tears away from the sun, and begins racing toward Earth at over 2 million of. This coronal mass ejection carries the magnetic field strength of 1 million Earth magnets and enough energy to power the United States for 20,000 years. Unlike the brief bursts of solar flares, these massive chunks of the sun's atmosphere can stretch across distances larger than the orbit of Mercury when they slam into Earth's magnetic field. They can compress it so violently that our protective magnetic bubble temporarily collapses on the side facing the sun. Coronal mass ejections happen when enormous loops of magnetic field lines extending far above the sun's surface become unstable and snap. Picture a soap bubble forming and then suddenly bursting. Except this bubble is made of milliandary plasma and measures larger than Jupiter. The magnetic field lines act like invisible cages, holding vast amounts of solar material in the sun's corona. The wispy outer atmosphere we can see during a total solar eclipse. When these magnetic cages break open, they launch billions of tons of charged particles into space in all directions. The fastest coronal mass ejections can travel at speeds up to 9 million of, crossing the 93 million mile gap between Sun and Earth in just 15 hours. Most take 2 to 4 days to make the journey, giving us some warning when space weather monitoring satellites detect them leaving the Sun. The 1989 Quebec blackout demonstrated how dangerous these solar storms can be for modern civilization. A moderate coronal mass ejection hit Earth and induced electrical currents in power transmission lines across eastern Canada. The power grid collapsed within 90 seconds, leaving 6 million people without electricity for 9 hours during a cold March night. Transformers overloaded and exploded, causing damage that took months to repair. The Quebec was just a preview of what a truly massive coronal mass ejection could do.